Welcome to another Mathologer video. Have a look at this strange square over there. What secrets does it hold? Well, let's see. Okay. So the pieces in the three rows all combine into the same square. Very cute. But actually not that hard to produce 9 pieces like that, right? Just cutting up the square into 3 parts in 3 different ways will do the trick. Okay, but there's more. Have a look. There. And so the pieces in each column also combine into the same square. Now that is super special. But wait, there's more. Can you guess what? Yep, the diagonals also combine into the same square. There, first diagonal and second diagonal. Wonderful! What we're dealing with here is some sort of geometric magic square. I'm sure that anyone who chooses to hang out at Mathologer is familiar with the Loshu magic square. Right? This age-old 3×3 magic square features the numbers from 1 to 9. For this square, all the rows, columns and diagonals add up to the magic constant 15. People have been fascinated by magic squares for thousands of years, and there is no shortage of those who believe that magic squares actually hold real magical power. Also, throughout the ages, among the many people obsessing about magic squares, there have always been quite a few of the top mathematicians. For example, these 3 mathematical superstars all spent a lot of time researching magic squares. There, that's Leonhard Euler on the right, Srinivasa Ramanujan in the middle, and Pierre de Fermat on the left. Here's one of the nice A×H magic squares discovered by Ramanujan. This square features the numbers from 1 to 64, and the magic constant is 260. Impressive and magical. But what's the source of this sort of number magic and the super impressive geometrical magic that I just showed you? Today's video was inspired by watching TV. No, really. An absolutely beautiful incorporation of my all-time favorite way of conjuring up magic squares appeared in the 2010 Korean historical drama series Tree with Deep Roots. This K-drama is loosely based on the life of the Joseon king Sejong the Great, who lived in the 15th century and was famous for creating the Korean alphabet. Today's video is also a double feature. In the first part, I'll show you the king's beautiful method for making magic squares, and in the second part, I'll give you an intro to the magic of geometric magic squares. Get ready, get set, enjoy! Okay, over there, that's the king in the TV drama. At the beginning of the story, he's still very young and really just a puppet king with no real power. The evil puppet master is his father, the former king. The young king's way of dealing with all sorts of bloodshed and slaughtering of the innocent perpetrated by his father is to retreat to his study and do some maths. Well, not just any maths, but magic squares. That's the study, and what he's working on there with an army of court lady helpers is a gigantic 33×33 magic square. Just like with the real problems in his life, he's really at a loss as to how to solve this monster maths problem. How to make all the rows, columns and diagonals add up to the same number. Well, the king's definitely not a beginner. On closer inspection of the room, we find a working 5×5 magic square. There's also a 7×7 and an 9×9. And on the other side of the room, out of sight at the moment, there's also the classic Loshu 3×3 magic square. Now, at that time, people in Korea were still using Chinese numerals. Really impressive how much attention to detail the filmmakers paid to getting all this right. For example, have a look at the shape of the tiles, which allow them to be manipulated remotely from the side of the room with these special pole tools. But if you actually know just a little bit about Chinese writing, you may notice 1 or 2 things that don't seem quite right. Can you spot the mini bloopers? Anyway, apart from the court ladies who manipulate the tiles, the king also made sure that there is some tech support at hand. These are the court ladies in charge of checking the row, column and diagonal sums. Have a look at the gigantic abacus over there on the right. I want one of those. Now, eventually, after a fair bit of mayhem and shedding blood, the king finally can't take it anymore and stands up to his father on a minor matter. This really infuriates his father, who then has a special lunchbox sent to his son. There, that's the lunchbox. Sending. Very pretty. And suspense, suspense. The sound opens it. Okay, open, open, and it's empty. What on earth does that mean? Well, everybody watching knows what it means. By sending the empty lunchbox, the father is commanding his son to commit suicide. Amazing parenting, right? Anyway, and it's just great the way this was done in the drama. And putting aside the minor issue of suicide commands, the special shape of the lunchbox also triggers a beautiful mathematical aha moment. Of course, the low shoe 3×3 magic square will fit nicely into the lunchbox like that. But also, opened up in this way, the overall shape of the lunchbox is that of a square inside a square. Can you see that? This observation somehow makes our king mathematician, who is not interested in the suicide thing, try something that he's never tried before. This is what he does. He moves the 1, okay, moves that, and moves that number. Can you see something amazing? There. 1, 2, 3, 4, 5, 6, 7, 8, 9. The 9 digits in natural order inside the larger square. What's going on here? The king also immediately recreates what he sees in his mind using the tiles of his physical low shoe 3×3. There. Okay. Whoa, nice, huh? And now he's got this idea that maybe something like this also works for larger magic squares. He first checks this for a 5×5 there. Okay. A checkerboard, 5×5 board, extended a la lunchbox. Now he fills in the dark squares with the numbers from 1 to 25 in their natural order. There, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Now he takes the corners that are sticking out and moves them inside the board like this. So first corner, move it in. A perfect fit. How nice. Do the same with the other corners. There, number 2, going in, fits. Number 3, and the last one. Okay. Whoa, very nice, huh? And yes, this really creates a magic square. All rows, columns, and diagonals add up to the same magic number, which turns out to be 65. And of course, the king doesn't stop there. After this, we see him experimenting with a 7×7 setup. Spent ages on Photoshop doing this one, but absolutely worth it. And it works. And then the king stops. Of course not. Now the army of court ladies spring into action, and it's a real treat to see the 33×33 magic square come to life. Have a look. There, finished. Now over to the tech support ladies. Okay, eventually, after a lot of abacusing and note-taking, the tech support supervisor, that lady there, declares all row, column and diagonal sums are equal, and therefore they've created a true magic square. Bit of a challenge for you. What's the magic constant of this magic square? And for the programmers among you, can you write an app that animates the king's construction for all odd orders up to 33? Anyway, this is a real mathematical breakthrough for the king, and also a real breakthrough. His mathematical success provides him with a general confidence boost, and his life starts picking up from that moment on. There's also a scene with the father tyrannically simplifying the construction of magic squares. Very funny and really well done. I'll include the relevant time codes in the description of this video. If you've got some time, definitely check out the whole drama. Well worth it. The king's way of creating a magic square really works for all odd size magic squares, 3×3, 5×5, 7×7, etc. On the other hand, it does not work for even order squares, 2×2, 4×4, 6×6, and so on. Well, just give it a try for the 4×4 and you'll immediately see what gets in the way of this method working for even order squares. Still, it works for odd orders, and once you know this amazingly simple method of making magic squares, you'll probably never forget it, right? But of course, the real question is, why on earth does this method always work? And it is the answer to this question that reveals the real magic and beauty of these magic squares. Also, figuring out the why is really what's missing in this story. Figuring out the why is a very big step up from our king's achievement, right? We want a mathematical proof that shows once and for all that this method always works. Once you've got such a proof, all those court ladies can retire. Okay, let me show you the heart of a really beautiful proof. Not hard, promise, and definitely worth the trip. To start, let's rewrite the numbers in this grid a bit. Okay, first diagonal, 1, 2, 3, 4, 5. Let's leave those first 5 numbers as is for the moment. Now, second diagonal, first is 6. Let's write it as 1 plus 5, next 7. That's 2 plus 5, and so on. So what we're doing here is thinking of the second diagonal as the first diagonal offset by 5. Okay. Third diagonal, 11, that's 1 plus 10. So here the offset is 10, 12 equals 2 plus 10, and so on. Next diagonal offset 15, and the last diagonal offset 20. And just to give everything a nice uniform look, let's think of the first diagonal as having offset 0 there. Okay, fantastic. Now let's collapse things back into the magic square. Okay. Let's now pick one of the columns and take a closer look. Let's pick the second column there. Now every entry of the magic square is written as a sum of 2 numbers. As you can see, all possible left sides, 1, 2, 3, 4, 5, are present in this column exactly once. The same is true for all the possible right sides. Each of the offsets 0, 5, 10, 15 and 20 is present in this column exactly once. This means that the sum of the column is equal to the sum of all possible left sides, 1 plus 2 plus 3 plus 4 plus 5, plus the sum of the possible right sides. This total happens to be 65. Cool. Now on closer inspection you can see that the same is true for all columns. For example, here is column 3. There, the numbers 1, 2, 3, 4, 5, all there on the left, as are the offsets 0, 5, 10, 15 and 20 on the right. Just in a different order than in the previous column. And the same is true for all columns and all rows. So a quick look at some rows. There, or there, and there, all there. How about the diagonals? Well, let's have a look. As you can see, 1, 2, 3, 4, 5 are all there. On the other hand, the right sides of these entries are all equal to 10. Of course, being the middle number of the offsets, 10 is also the average of the offsets. So 5 times that average equals the sum of the offsets. And so overall, we also get 65 as a total for this diagonal. Similarly for the other diagonal. Here, all the right offsets are present. And we get 5 times the average 3 of 1, 2, 3, 4, 5. And so we get 65 again. That's all really, really nice, don't you think? And so what we want to prove is that the same beautiful internal structure is also present in all the other square tables of numbers that our King's method produces. Once we've done that, we'll have proved that all of these square tables are actually working magic squares. Okay, let's do it. To be able to illustrate to you as concisely as possible what's going on under the hood, I'll stick with this 5 times 5 square. But everything I'll say will apply to any size odd square. Okay? Let's pick one of the entries of the square, say this one. And here's the entire row for that entry. What we'll show is that in this row, none of the other entries can have the same left side 3 or right side 5. As I said, our argument will be completely general and will, in essence, apply to all entries of this row, and indeed any row or column of any square table of numbers created like this. This means that our argument will show that all left sides of all the entries in a row are different. In turn, that means that all possible left sides have to be present in this row. Similarly, our argument will show that all the right sides are different, and so all possible right sides also have to be present. And that will pretty much complete the proof, at least for the rows and columns to add up to the same number. All okay so far? Great. Now, just in case you get a little bit lost, no problem. Just try to get the gist of what's going on. And remember, there's this thing called rewind. Anyway, as I said, it all boils down to seeing clearly why the left and right sides of our chosen entry are different from the left and right sides of all the other entries in the same row. Okay, let's uncollapse our square. Remember, we're interested in this row of the final table. Now, look at the 4 visible entries of this extended row. They're all clearly different, right? It's also clear that all of these entries, including the ones on the outside, will end up in our chosen row after collapsing. Right? So after collapsing, no duplication will arise from the entries that are currently sticking out on the left and right. Cool. Now the row we're interested in is located above the middle horizontal line. This means that after collapsing, the entries that are currently sticking out at the top can never end up in our row. I just dip below. So no danger there. Okay, what about the entries sticking out at the bottom? Can they lead to duplication of the 3 on the left or the 5 on the right after collapsing? Well, let's see. Since we're dealing with a 5 times 5 square, when things collapse, entries that move will move by exactly 5 squares. So any entry that ends up in outside the row must have come from exactly 5 rows below, right? So whatever moves up into that row must be 5 below. On the other hand, the entries with the same first part 3 as our 3 plus 5 entry are all in this diagonal here, and the entries with the same second part 5 as our 3 plus 5 entry are all in this diagonal here. Okay? Now these diagonals also both comprise 5 numbers, right? 1, 2, 3, 4, 5, that's 5 numbers, and 0, 5, 10, 15, 20, that's 5 numbers. Okay? And our 3 plus 5 entry being part of both diagonals means that neither of these diagonals can possibly reach more than 4 below our row. And this means game over. Since the extra entries that concern us are exactly 5 rows below, the critical diagonals never reach that far down. Consequently, when we move in the entries at the bottom, we can be sure that none of them will create any trouble for us. So what we've shown is that for our 3 plus 5 entry, no other entry in the same row will have either the same first part or the same second part. The same argument takes care of all the entries above and below the middle row. For entries in the middle row and those that are currently outside the central square, the argument has to be modified a bit, but is basically the same. Anyway, I hope you liked my sketch of this beautiful proof. Of course, the King's beautiful method is not really the King's method. It's due to the 17th century mathematician Claude Gaspard Bachet de Mézières. If I ever decide to grow a mustache, I want this one. Doesn't seem very likely, does it? Remember, I mentioned earlier that there were also 5 times 5, 7 times 7 and 9 times 9 magic squares on display in the King's study. We actually do get a close-up look of these 5 times 5 and 7 times 7 squares, and I also had a very close look at those because I was curious as to whether they actually used magic squares constructed with Bachet's method, which would have amounted to a bit of a blooper. Well, it turns out that these magic squares are constructed in a different way. For example, here's the 5 times 5. As I said, it's not constructed using Bachet's method, so no immediate blooper there. However, on really close nitpicking inspection, there is a bit of a blooper after all. It turns out that this magic square is built using another general method that also gives magic squares for all odd order squares. In this method, the numbers from 1 to 25 are placed into the square in their natural order like this. There's the 1, 2, 3, 4, and so on. If you're up for a bit of a challenge, you can figure out how exactly the second method of building magic squares works. Leave your thoughts in the comments. What about the 7 times 7 in the study? Is it built using the second method? Actually, no. In fact, I did not recognize the method used for constructing this 7 times 7 magic square. Maybe one of you knows. All right, enough with K-drama magic squares. Let's move on to part 2 of this video and those amazing geometrical magic squares. Ready for our second story? Great, let's go for it. Over there is the cover of a super nice book about geometric magic squares. It's by magic square master Lee Sallows, the inventor of these amazing constructs. Most of what I'll talk about in the following I've actually learned from his book. Highly recommended. I had not thought about magic squares for decades until I was prompted by that K-drama to have a closer look at what's new. Pretty much the only thing that I had not seen before and what I found really intriguing were these geometric magic squares, or, wait for it, geomagic squares. Nice name, huh? And since this will probably be my only ever mythology video on magic squares, let's do it all. So I also want to share with you some of the magic of these constructs. Let's start with a couple of interesting observations about geomagic squares. First, when you measure the areas of the pieces in a geomagic square, you get a square table of numbers in which all horizontals, verticals and diagonals sum to the same magic number. Obvious, right? And if you're lucky, you may be able to scale things just right for all those areas to be integers. For example, let's put a grid on top of our pieces over there. And let's say every one of the little squares has area 2. Then each of the 9 pieces turns out to have integer area. And as it happens, all of these integers are different. This means that underlying the geometry is a bona fide magic square. Of course, it's a little different. Previously, all our magic squares had this special feature that the integers in the square went 1, 2, 3, 4 up to the appropriate square integer. But according to the International Committee of Magical Mathematics, I made that one up, this special property is not required for a magic square. Fair enough? Anyway, if you object, you can write to the committee. To repeat, for a magic square, we just need that the entries are distinct positive integers, that all rows, columns and diagonals add to the same magic number. Okay, second observation. It turns out to be really easy to convert any magic square into a geomagic square. For example, start with a standard 3 × 3 magic square. Now, just replace every number by a rectangle consisting of the same number of little squares, like that. Now all the rows combine into the same long rectangle, and so do all the columns and diagonals. There, the columns. Impressed? No? Well, that's okay, we'll get there. Anyway, since every magic square can be thought of as a geomagic square, we can hope that in a potentially larger world of geomagic squares, some extra magic might occur. And this really turns out to be the case. Here are 2 more examples of geomagic squares having some nice properties that I find particularly remarkable. For my first example, let's rearrange those rectangles over there into different shapes by moving around the little squares. There, magic wand. Real magic. Now recall that the magic constant for the standard 3 × 3 magic square is 15. And 15 little squares is just enough to make a 4 × 4 square with a little bite taken out. And that's what we'll do. The 4 × 4 square with the bite is our magic constant shape, like that. That really all works out. Very, very cute. Impressed now? Still no? I don't believe you, but let me make absolutely sure that everybody watching is really impressed. There's something extra special about this set of pieces. Ready? Take any of the numbers that add up to 15. For example, these 4 here. 2 + 4 is 6, 6 + 1 is 7, 7 + 8 is 15. Altogether, 2 + 4 + 1 + 7 is 15. Then the corresponding pieces also combine into the square with the bite. Wow. Now that is extra special. Here's another combo. 7 + 1 + 3 + 4 is also 15. Fantastic. Now on to our second example. Probably the second most famous magic square after the standard 3 × 3 is the one in this drawing by Albrecht Dürer. Many of you will be familiar with this drawing. You can see the magic square up there in the right corner. Dürer's magic square features the numbers from 1 to 16 and has magic constant 34. Well, that could be a 6 × 6 square with 2 bites taken out. And here's a geometric counterpart of Dürer's magic square that just does that. Really magical. Great, don't you think? Okay, so how do you come up with non-trivial geometric magic squares? Well, Lee Sallow was inspired by a famous formula for 3 × 3 squares, this one here. Choosing any integers a, b, c, the formula gives a square table of integers, all of whose rows, columns and diagonals add up to 3 × c, the number in the middle of the table. Choosing a is equal to 1, b is equal to 3 and c equals to 5 gives you the standard 3 × 3 magic square. In fact, you can get all 3 × 3 magic squares like this. However, not all choices of integers for a, b and c will give magic squares. Why not? Well, the International Committee of Magical Mathematics has declared that all entries in a magic square must be different, remember? And for example, choosing both a and b equal to 0 and c is equal to 1 will make all entries equal to 1. Not terribly magical, right? Anyway, Lee Sallow's great idea was to replace a, b and c by shapes and then reinterpret the addition as joining shapes and the subtraction as carving one shape out of another. And after playing around with this idea a bit, he came up with a working non-trivial example. So A is a little semicircle, B a little rectangle, and C a larger square. Then for C minus B, for example, he carves the little B rectangle out of the C square like this. Next, C plus A plus B. For this he joins the A semicircle and the B rectangle to the C square like this, and so on. Now these pieces really combine along all rows, columns and diagonals into the same shape. Really quite marvelous. Let me show you the rows there. First row and second row, same shape, and third row, again, same shape. And once you've found a solution like this, you've actually found infinitely many solutions. Why? Because the exact shape of the ABC pieces doesn't matter too much. For example, you could replace this rectangle by a little triangle, resulting in different pieces, which still combine in exactly the same way. They are all triangles now instead of rectangles. And by making suitable variations, it's possible to come up with pieces whose shapes make it pretty much impossible to guess how they were constructed. Here's an example, right? If you see these pieces in the wild, you'd never guess where they come from. Well, let me show you the corresponding choices for A, B, and C. And just to demonstrate, here's how the rows still combine into the same large T shape, just as before. There, T shape. There, T shape. Just nice the way these combine, right? Okay, magic, magic, magic. And here's another spectacular example that uses the magic square equation. This time a 3D one. Super pretty, isn't it? Wouldn't it be nice to turn this into a physical puzzle? So make a set of those nice pieces from little wooden cubes, arrange them into a 3x3 squares as over there, and puzzle out how exactly the pieces in all those rows, columns and diagonals combine into the same 3x3x3 cube. Then we'll show you how the pieces in the first row combine. There. Take this piece, put that one on top, and then it just fits in. Cool. What other ways are there to come up with these geometric magic squares? Well, what do you think? Computers, of course. These days, one of the first things anybody would try is to do some computer searches. For example, to come up with nice geometric counterparts of the standard 3x3 over there, start with a list of the basic shapes that can be pieced together from 1, 2, 3, 4, 5, 6, 7, 8, and 9 little squares. There, those are the different kinds of pieces made up of 1 to 5 little squares. The number of different pieces increases as the number of little squares gets bigger. At the top, there are 1,248 different pieces consisting of 9 little squares. Anyway, for a geometric counterpart using these pieces, there's only one choice for the 1. It's going to be this one. Same for 2. With 3, there are 2 blue choices. With 4, there are those 5 green choices. 12 red choices for 5, and so on. Then multiplying all those numbers together gives the total number of sets of pieces to consider. That's a lot of possible sets of pieces. Okay, now let's pick a nice shape consisting of 15 little squares, say a 3x5 rectangle. Then it's easy to check whether any of those possible sets of pieces actually is a geometric square with this 3x5 as magic constant shape. Well, it turns out there is. In fact, and this is really quite surprising, 1,411 of our sets of pieces are magic squares that have the 3x5 rectangle as their magic constant shape. Wow, 1,411 different geometric squares. But if you think that's a lot, actually that's nothing compared to the numbers of geometric squares you get for other magic constant shapes. Have a look. So there are almost 30,000 different magic sets of pieces that combine into that last 4x4 square with one corner missing. Pretty amazing, right? In fact, these large numbers of solutions for different magic constant shapes prompt another question. Is there perhaps a bimagic square? A set of tiles that has two completely different magic constant shapes? What do you think? Well, turns out there is. This is the set of pieces that I showed you before. It has the 3x5 rectangle as a magic constant shape. However, it actually has a second magic constant shape, that one here. So all rows, columns and diagonals combine into two different magic constant shapes. In fact, and this is really crazy and unexpected, this set has a total of 12 different magic constant shapes. Before I show you the other magic constant shapes, let me say goodbye for today. Let me know what you thought of today's topics in the comments and follow the links in the description for a lot more information about everything I talked about today. Until next time.